Well, welcome back to another rousing rendition of Basic Chemistry, Chapter 11, 11.10, last part of this chapter. So we're going to use Dalton's law of partial pressure to calculate the total pressure of a mixture of gases. All right? Sounds complicated, really isn't. So we'll figure this out. All right? So partial pressure of a gas is the pressure of each gas in a mixture. Is the pressure that gas would exert if it were by itself in the container. So it's almost like that separation of the gases. Like if we looked at the atmosphere, made up of nitrogen, argon, carbon dioxide, and oxygen, blah, 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 blah. It's talking about separating those out and how much pressure each one would exert if they were individually in the container. All right. So Dalton's laws of partial pressure states that the total pressure depends on the total number of gas particles, not the types of the particles, but the total number of the particles exerted by a gas mixture is the sum of the partial pressures of those gases, which makes sense, okay? So P sub T is our partial mixture of or is the total pressure of our gases, of the gas mixture, and then P1, P2, P3, P4, P5, P6, P7 is the sum of the partial pressures of the gases to equal the total. So that's pretty logical, okay? So right here we've got an example of a single volume, okay? So we have helium at 2 atmospheres in this container, and then we have argon in this container at 4 atmospheres. Now, if I were to simply put helium and argon in the same amounts into the same size container they're individually in, it's just an additive effect. 2 plus 4, well, yeah, what's 2 plus 4? Well, that equals 6, right? Just like that equals 6. So, the air you breathe is a mixture of gases, typically a mixture of the gases in air include nitrogen, oxygen, carbon dioxide, argon, and water. Forgot about water. There we go. Water as a vapor. And if we look up into the air, what do we see? We see clouds. And what are clouds made of? Water vapor. Anybody that's ever flown through a cloud in a storm on a plane, or just flown through a cloud, doesn't have to be in a storm, well, you'll see little water droplets on your windows. Well, why? Because you just went through water vapor. So, guide to calculating partial pressure. Write the equation for the sum of the partial pressures. Rearrange the equation to solve for the unknown pressure. Substitute the known pressures into the calculation, or into the equation, and calculate the unknown pressures. Organize, rearrange the formula, and plug and chug. So whenever you think substitute, I want you to think plug and chug. All right, so a scuba tank contains oxygen with a pressure of 0.45 atmospheres and helium at 855 millimeters of mercury. What is the total pressure in millimeters of mercury in the tank? All right, well, they're throwing you off. They're trying to go, oh my gosh, they're adding atmospheres and millimeters of mercury. Well, we know the constant, right? 1 atmosphere equals 760 millimeters of mercury. So we can either convert atmospheres to millimeters of mercury or millimeters of mercury to atmosphere, right? It's no issue. So write the equation. So with the pressure of oxygen plus the pressure of helium equals our total pressure. So we rearrange the equation, okay? So we first need to, and actually we don't have to rearrange anything because we're solving for what? What is the total pressure in the tank? Well, sweet. We've got 2 items, but we've got to match up our units. So we're going to choose to convert the helium from millimeters of mercury to atmospheres. Simply 855 millimeters of mercury over 760 millimeters of mercury is going to give us 1.12 atmospheres. Scuba tank contains oxygen with a pressure of 0.45 atmospheres, and then helium 855, all right, converted to 1.12, so we simply go 0.45 plus 1.12, giving us 1.57 atmospheres. That is the pressure in the tank. Seems scary. Very, very easy once you know where to arrange everything. So, gas produced in a laboratory usually contains water vapor, okay? So now we need to know water vapor pressure and the gas pressure. As a partial pressure obtained, subtracting the vapor pressure from the water pressure. So we want to know what the gas pressure is, all right? So in this reaction, magnesium reacts with hydrochloric acid to produce hydrogen gas. So magnesium, 2 moles of hydrochloric acid, aqueous, okay, equals magnesium chloride, which is aqueous, and then hydrogen, okay? So as H2 gas is produced, it's displaced some of the water in the container. The gas collected will be a mixture of hydrogen and water vapor. So we're going to have to sort that out, right? All right. So we use vapor pressure of water at the experimental temperature to determine the amount of dry hydrogen gas produced during the reaction. So we can see this little collection vessel right here, right? We've got this collection vessel. And what we see is the reaction of the magnesium with the hydrochloric acid. So the hydrogen and water vapor are going to be contained in this container, all right? So we need to obtain the vapor pressure of water, subtract the vapor pressure from the total pressure of the gas mixture to give the partial pressure of the needed gas. Use the ideal gas law to convert piece of gas to moles or grams of gas collected. All right, so how do we do this? All right, well, when magnesium reacts with HCl, volume of 0.355 liters of H2 gas is collected over the water at 26 degrees Celsius. The vapor pressure of water at 26 degrees Celsius is 25 millimeters of mercury. If the total pressure is 752 millimeters of mercury, how many moles of H2 gas were collected? All right, so we definitely need this equation, right? We need to write this down. My guess is we're going to have to figure out some molar masses and all that good stuff. So you may want to get ahead and start collecting. Okay, so first step, obtain the vapor pressure of water. Okay, the vapor pressure of water at 26 degrees Celsius is 25 millimeters of mercury. This is, how do we know this? Well, it was given to us, right? See it right up there? Yep. So we know this. It's a constant. And you can actually obtain this data on different data tables. All right, so we've got our total, right, of pressure. And then we've got a total of hydrogen plus oxygen to give us our total pressure. We only want to know the hydrogen. So what we have to do is subtract out the water pressure from the total pressure, leaving us with the pressure of the hydrogen. So that being said, it gives us 752 minus 25, leaving us with 727 millimeters of mercury. That is our hydrogen pressure. Now we need to decide, how do we convert this information that we've gotten into moles? How much do we have? All right, we go back to our ideal gas law, PV equals nRT. So we're going to look for moles, so it's going to be PV over RT. And in most of the questions and equations that you'll use, it's normally you're searching for moles. You could be searching for other things, obviously, but you'll notice that we've been doing that. All right, well, so how do we solve for moles of hydrogen gas? So we go ahead and take our pressure of hydrogen times the volume, so 727 times 0.355, okay, liters, and divide that by our constant in millimeters of mercury, right, which is 62.4 versus 22.4 atmospheres of liter, because we want to stay consistent. And then times 299. Well, how do we get 299? Well, our temperature, 26 degrees plus 273, gives us is in Kelvin. When we do the calculation, we end up with 1.3 times 10 to the negative 2 moles of hydrogen. All right. So, and then can we convert those moles of hydrogen to grams? Most definitely. We've got, all we have to do is take the molecular mass of H2, which is approximately 2 grams per mole, and then we would go ahead and multiply the moles we have by the molecular weight, and we would end up with grams. All right, so how does this link to our health? All right, during breathing, an exchange of gases occur in which oxygen from the air diffuses into our lungs and into our blood. Carbon dioxide is produced in the cells and carried to the lung to be exhaled. So we're inhaling in oxygen and probably some water vapor, and exhaling carbon dioxide and probably some water vapor. Okay. And table 11.8, partial pressures are given for the gas in the air that we inhale, inspired air, and then air into the alveoli. Yeah, I just learned about that this morning, actually. And air that we exhale, expired air. Okay. The partial pressure of water vapor increases within the lungs because the vapor pressure of water is 47 millimeters of mercury at body temperature. Okay. Remember, we have vapor in us. All right. So if we look at partial pressure gas during breathing, we've got the nitrogen, we've got oxygen, we got carbon dioxide, we got water vapor. So when we bring it in, we're bringing in nitrogen, oxygen, carbon dioxide, and then water vapor. All right. Then the alveoli air, Lisa, you can kill me about that pronunciation later, will equal, we have nitrogen, oxygen, and carbon dioxide and water vapor because we got this exchange going on, so these things are moving back and forth. And finally, when we exhale, we've got 569 of nitrogen coming out. You'll notice that the oxygen obviously decreases, but what happens to the carbon dioxide? If we look over here, the carbon dioxide is going up, right? And that would make sense because that's how our bodies work. Now, if we were doing a calculation on plants where what they do is bring in carbon dioxide and then they expel oxygen, we would see the exact opposite relationship. So this is your heart, and there's some lungs, your little sacs that bring in air, and then there's some cellular stuff going on. And yeah, I don't know. I'm not a biologist, never will be. It's weird, but yeah, you can see the exchange. Oxygen in, CO2 out. All right. So these are the concepts. You should have got all this, okay? Yeah, we've covered all these. Okay, so we got Boyle's Law, Charles' Law. Boyle's Law's relationship of pressure and volume, Charles' Law, volume and temperature. Gay-Lussac's Law, pressure and temperature. Combined gas law, pressure, volume, and temperature. And then the ideal gas law, and pressure and volume is equal to moles that are constant times temperature. Okay? And Avogadro's law we can use to find molar volume, molar mass, gas mixture, partial pressures. This concept map is something you may want to jot down into your notes to how you can kind of interrelate and actually pull all this together. So this is chapter 11. I hope you're feeling good about it, and rock on.